Hello everyone, my name is Samantha and I'm currently a PhD student at the University of Pretoria, South Africa. Today I will be speaking on my master's dissertation titled Shape Analysis of the Zygoma to Assess Ancestry and Sex Variation in Modern South Africans. Skeletal remains exposed to an outdoor context or prone to post-mortem damage and fragmentation, making skeletal analysis difficult for the anthropologist. Research on ancestry and sex from isolated fragments of the cranium is necessary to improve identification of fragmented remains. The zygoma has proven to be more durable post-skeletonization than other cranial bones, making research relevant into the variation within the zygoma. Whilst the shape of the zygoma has been studied in a South African population using morphological, metric, and geometric morphometric techniques, these studies did not include Indian South Africans. The purpose of the study was to assess the shape variation of the zygoma attributable to sexual dimorphism and ancestral variation among South Africans, including Indian South Africans, using a geometric morphometric approach. A sample of 400 three-dimensionally reconstructed models from head CT scans of black, colored, white, and Indian South Africans were used with an equal sex and ancestry distribution. The original CT scans were anonymized to remove any identifying patient information, and only the demographic information necessary for the study was recorded. Only scans of individuals older than 18 years were collected. Any skull reconstruction with pathological changes, trauma, supernumerary sutures, obliterated sutures, or imaging artifacts that prevented the placement of landmarks were excluded from the study. The CT scans were opened in a visa 9 and orientated in the Frankfurt horizontal plane. Once placed in the correct orientation, the scans were uploaded into the program called TIFME, where the 3D skull models were segmented from the surrounding tissue. Once the models were segmented, the meshes were uploaded into Visa 9 and smoothed for better viewing. The next step involved the manual placement of landmarks on the segmented skulls. 11 landmarks previously described in the literature were used for the analysis. The landmarks were placed onto each specimen in a Visa 9 where the order of landmarks was kept consistent across all specimens. The image depicts the set landmarks used for the study in the anterior view, and this is just a zoomed in version so that you can better see the landmarks. This is the lateral view depicting the rest of the landmarks used on the study, as well as a zoomed in version so that you can better visualize where the landmarks are. The semi-landmarks were created in a Visa 9 and then converted into 80 semi-landmarks spanning each zygoma. However, because the zygoma has multiple curves that make up the entire shape, a specified number of semi-landmarks per curve of the zygoma was created to ensure homology. And as you can see in the image, the entire zygoma was outlined. To test for intra and intra-observer repeatability, dispersion analysis was used. Dispersion analysis calculates the distance between the repeated landmarks and the mean of the landmark. Based on craniometric literature, a deviation from the mean of less than 2 mm was deemed acceptable. Mean values less than 2 mm were obtained for both intra and inter-observer errors for the landmark and semi-landmark coordinates, indicating repeatability and reproducibility. A larger mean and standard deviation were obtained for the inter-observer error for both landmarks and semi-landmarks than for the intra-observer error. For the ancestral variation, a Procrustes ANOVA was used to test for significant differences amongst the population groups using the landmark and semi-landmark coordinates. The results of the Procrustes ANOVA with pooled sexes showed significant differences among black, colored, white, and Indian South Africans. A Procrustes ANOVA was also used to assess the ancestral variation when males and females were assessed separately for the landmark and semi-landmark coordinates. The results of the Procrustes ANOVA for males and females showed significant differences among the population groups for both sexes. A pairwise comparison was then performed as a post hoc test to assess where the significant differences occurred amongst the populations. Overall, white and Indian South Africans demonstrated more similarities compared to other population groups, except for males using the landmarks, where colored and Indian South Africans demonstrated more similarities. Wireframes showed that shape differences are present among the population groups. Black and white South Africans demonstrated differences between the length of the zygomaticomaxillary suture and the zygotemporal suture. The inferior border of the zygoma as well as the inferior margin of the orbit also differed between these populations. Black and colored South Africans showed differences at the inferior margin of the orbit, where the inferior margin of the orbit extended more inferiorly in colored South Africans than black South Africans. The zygotemporal suture also extended more laterally in black South Africans than colored South Africans. When black South Africans were compared to Indian South Africans, differences were noted at the zygomaticomaxillary and zygotemporal sutures. The zygomaticotemporal suture appeared to be shorter in Indian South Africans, while the suture extended more posteriorly in black South Africans. White and colored South Africans were also compared and revealed major similarities except for the length of the zygomaticomaxillary suture and the inferior margin of the orbit. White and Indian South Africans also revealed remarkable similarities, only differing slightly at the posterior margin of the frontal process. And lastly, colored and Indian South Africans revealed similar wireframes except where the colored South Africans indicated a more superiorly projecting frontal process and a slightly more posteriorly projecting zygomaticotemporal suture. A discriminant analysis was conducted to assess the discriminatory strength of the landmarks and semi-landmarks when used to estimate ancestry with the sexes pooled. Both males and females were combined, and only ancestral variation was assessed. All 26 PC scores were used and accounted for 100% of the variation. The results of the initial LDA showed a 65.48% accuracy. A backward stepwise selection was then used to remove any superfluous variables, and the results showed an overall correct classification rate of 64.5%. Leave one out cross validation was performed and yielded a correct classification rate of 53.8%. Overall, black South Africans classified better than the other population groups, with black female South Africans obtaining the highest correct classification rate. The Indian South Africans had the overall lowest correct classification rate, with the Indian females obtaining the lowest classification rate. The discriminant function using the semi-landmark coordinates to assess the ancestral variation yielded a 63% accuracy. After backward stepwise selection was used, an overall correct classification rate of 64% when estimating ancestry was obtained. A correct classification rate of 55.07% was achieved when leave one out cross validation was performed. Overall, black South Africans again obtained the highest correct classification rate. When looking at individual correct classification rates, black male and female South Africans had the highest classification rates, while colored South Africans obtained the lowest accuracy. Procrustes ANOVA was run on the generalized Procrustes coordinates of the landmark coordinates to test for significant differences between males and females. The results of the Procrustes ANOVA when all population groups were combined revealed significant differences between males and females for both set landmarks and semi-landmarks. However, as differences were noted in the general degree of sexual dimorphism among the various population groups, further Procrustes ANOVA tests were used to assess the sexual dimorphism of the black, colored, white, and Indian South Africans separately. The results showed that all population groups demonstrated significant differences between the sexes except for the colored South Africans that had a p-value of 0.107. The wireframes of the average zygoma shapes of the males and females when all population groups were combined show that females have a shorter zygomaticomaxillary suture, whereas zygule extended more inferiorly. The zygomaticotemporal suture and the inferior border of the zygoma also show differences between males and females. The lateral margin of the orbit extended more inferiorly, and the frontal process extended more superiorly in females compared to males. A discriminant analysis was run on the landmark coordinates to assess the discriminatory strength of the landmarks when used to estimate sex. All population groups were combined, and only sexual dimorphism was assessed. All 26 PC scores, which was 100% of the variation, were used to run an initial analysis, and the resulting LDA produced an average accuracy of 74.87%. A backward stepwise selection was employed to remove superfluous variables and resulted in an overall classification accuracy of 77.66% when estimating sex. Leave one out cross validation was then used and yielded a classification accuracy of 73.4%. The analysis demonstrated a female bias, where the females classified better than the males. An exploration of the classification matrix demonstrated that among the females, colored females classified the best, while black females classified the best among the males. while black males classified the best among the males. Colored South African males and black South African females had the lowest correct classification rates. Results of the LDA for the semi-landmark coordinates showed an overall correct classification rate of 78.9%. A backward stepwise selection resulted in an overall correct classification rate of 79.4% when estimating sex. Leave on out-cross validation was then performed and yielded a correct classification rate of 76.9%. Overall, females performed slightly better than the males, where colored females classified the best among the females and black males classified the best among the males. Results revealed that the most variation for both sex and ancestry is attributable to the zygomaticomaxillary suture. Leandi et al. Showed that significant differences were present between black, white, and colored South Africans for the zygomaticomaxillary suture shape. While the study conducted by Leandi et al. Analyzed the shape of the zygomaticomaxillary suture, the current study did not. However, inferences can be made that the location of the landmarks on either end of the suture may differ depending on the shape of the zygomaticomaxillary suture. Additionally, the current study demonstrated differences at the zygomaticomaxillary suture, zygotemporal, and frontomalar sutures. Differences were also noted along the lateral margin of the orbit with a more inferior placement in females, which is consistent with previous research. Overall, females appeared smaller than males. However, the study did not compare centroid sizes, indicating that some of the differences observed could be due to size differences between males and females. The differences observed between sexes may have also been caused by the extended maturation period in males compared to females. Evidence suggests that the extended growth of the zygoma in males causes a larger zygoma and more laterally displaced zygomatic arch in males compared to females, further explaining the more laterally projecting zygomaticotemporal suture in males. Significant differences were noted between sexes for all groups except colored South Africans. The nasal aperture of black, colored, and white South Africans indicate that white South Africans have a higher degree of sexual dimorphism, whereas colored South Africans have a lower degree of sexual dimorphism, consistent with the results obtained in the current study. However, research on the postcrania of black, white, and colored South Africans indicate that colored South Africans have a higher degree of sexual dimorphism, and white South Africans have a lower degree of sexual dimorphism, with black South Africans intermediate, inconsistent with the current results. The contradictory results of the crania versus the postcrania of the population groups may be because colored South Africans have contributions from indigenous Khoi and San populations, Asian populations, Bantu-speaking Africans, and Europeans. Furthermore, the crania of white females misclassifies males more frequently than the postcrania, demonstrating the differing levels of sexual dimorphism of the populations. In conclusion, through the use of geometric morphometrics, the shape of the zygoma demonstrated differences among the population groups and between the sexes, except for colored South Africans that demonstrated no differences between males and females. Furthermore, the zygoma demonstrated differences at all three sutures as well as the inferior margin of the orbit for both sex and ancestry, and that extensive overlap between the population groups occurred mostly between colored, white, and Indian South Africans. Black South Africans showed little with in-group variation and little overlap with the other population groups. Classification accuracies using linear discriminant function for sexual shape dimorphism and ancestral variation of the zygoma indicate that the shape of the zygoma may not be useful in classifying an unknown individual according to ancestry and should only be used in conjunction with other methods. However, the shape of the zygoma would be useful for estimating sex. While the use of CT scans aided in the assessment of the shape of the zygoma, sutures were often difficult to visualize, making data acquisition difficult. The use of other imaging methods such as micro-CT and CBCT scans may help overcome the limitation and provide a better resolution to visualize sutures in further research. The sample also consists of individuals who self-identified as a particular population group, which could have led to misleading results. Furthermore, the study highlighted the need for further evaluation of the Indian South African population group so that a better understanding of the variation within the population group and between the population groups of South Africa can be done. The analysis of the zygoma to further assess the effect of diet, climate, and symmetry may aid in further understanding the shape of the zygoma for future applications in anthropology as well as in medical fields. Thank you. References are available upon request.